Now in this section, we'll be discussing how a chromatogram can be evaluated and how we can take some parameters or quantitative measures to look at a chromatogram to tell us if the results are good or not. So the first measure we'll be talking about in detail is this idea of resolution. Now resolution comes from the word resolved, and it is a measure of two adjacent peaks and whether they are well separated or not well separated. Of course, in any good chromatogram, we would expect that every pair of adjacent peaks are sufficiently separated so that we can identify the individual chemical components and also quantify these individual chemical components. So resolution is a measure of the extent of separation between two adjacent chromatographic peaks. And if we look at the equation, we'll see that in the numerator is actually the two retention times. So it's the retention time of the peak B minus the retention time of peak A, which is the less retained compound. So these retention times are typically measured in minutes, and intuitively this would make sense because the greater the difference in retention times, certainly the better the resolution of the two peaks are. In the denominator, we see that we have the sum of the two peak widths. Now, of course, the narrower the peaks, the better the resolution is going to be, because if the peaks are very narrow, then the peaks are very unlikely to overlap, and therefore they are more likely to be very well separated. If the peaks are very wide, then there is a high chance that they will be overlapping and therefore not well separated. So therefore, the wider the peaks, as the term is in the denominator, the wider the peaks, the lower the resolution will be. So this equation actually simplifies to 2 times the difference in retention times, that's the numerator, and then divided by the sum of the peak widths in the denominator. So clearly, again, if we have a more significant difference between the retention times of the two peaks, naturally the peaks will be better separated, which leads to better resolution. And from the denominator, if we see that the peak widths are very small, again, that will give us better resolution because very narrow peaks are very unlikely to overlap with each other. So this is an example that we've seen this chromatogram earlier, whereby our two peaks, the peak A and peak B, are clearly quite well resolved, so they are quite well separated. So of course, the calculation of resolution for these two peaks will be the difference in retention times. So it will be TR of B minus TR of A as the numerator term, and 2 times of that divided by the sum of the peak widths. So we would take the peak width of A plus the peak width of B, and that would be our denominator term for the calculation of resolution. So we have to give some kind of benchmarks for resolution in order to determine whether the resolution between two given peaks is sufficiently good for identification or quantification. So generally speaking, we say that if resolution is calculated to be 1.5 and above, that means that the separation is very good, and therefore we will have no problem identifying the individual chemical components or even quantifying the individual chemical components. Between 1.2 and 1.5, the resolution is actually okay, which means that although the peaks may be somewhat close together, but we will still be alright in terms of identifying the various components and trying to quantify. However, if we have the resolution calculated to be below 1.2, then we typically say that the separation is not good enough in order to identify or quantify the individual components. So earlier, I already mentioned that if we have a greater retention time difference between two peaks. Of course, logically, this results in better resolution, right? Because the peaks are further apart based on their retention times. And of course, if the peaks are very narrow, this is what we like. When we have narrow peaks, we are very much more likely to have good resolution and our peaks not overlapping. So this is a quick example on analysis of lemon oil, where we have two compounds, the first having a retention time of 8.36 minutes and the second having a retention time of 9.54 minutes, and the two widths for these two compounds are 0.96 minutes and 0.64 minutes respectively. We're asked to calculate the resolution, so quite simply we would use the formula 2 times the difference in retention time divided by the sum of the peak widths. So 2 times 9.54 minus 8.36, and then that whole term divided by the sum of the peak widths, which is 0.96 plus 0.64. So this resolution calculates out to be 1.475. So clearly it is greater than 1.2, which means that it is certainly sufficient for identifying or quantifying the individual compounds. Although it is somewhat less than 1.5, right, which is the threshold number that represents a very good or ideal separation. So we're going to further talk about some column characteristics and how we can calculate some various parameters that will tell us a little bit about whether a column is suitable for that particular analysis. So we have three factors that we can calculate, and these we can use to determine if a column is suitable for that particular analysis. The first is retention factor. So retention factor describes quite simply how much the various components are retained in the column. Obviously, when we use a certain column, we want to generate retention because only with retention of the various chemical components can we end up with decent separation, right? So we need to take a look at the retention factor to see whether it's sufficient for the various components in the sample. That will lead us to the ability to generate separation. Another important factor is the selectivity factor, and this is the ability of the column to differentiate two peaks or two chemical components. So the selectivity factor will actually measure the retention factors for two adjacent peaks, and that will give us an indication of whether the column is able to differentiate between these two peaks. Of course, each of these three column characteristics we'll describe in a bit more detail in the upcoming slides. So the third factor we'll talk about is separation efficiency. Now, separation efficiency is the ability of a column to give us narrow peaks. Earlier, I've already mentioned that narrow peaks are very desirable because narrow peaks tend to lead to good resolution. If your peaks are all very narrow, then it's very unlikely that they will overlap, and therefore they should tend to be quite reasonably well resolved. So we'll describe each of these column characteristics or column suitabilities as we progress. So the first thing I would like to define is this idea called dead time. Now, if you look at the diagram, you see TR, which is the retention time of the first chemical component. Of course, we also have the retention time of the second chemical component and the retention time of the third chemical component. Now, each of these chemical components are retained to some extent on the column, and that's why they eventually end up with certain retention times. But if we have the pure mobile phase that's flowing through the GC instrument, so we're talking about the pure helium gas or the nitrogen gas, it already takes a finite amount of time for this nitrogen gas or helium gas to travel through the column and to reach the detector, right? So even though it is completely unretained on the column, so it has no interaction with the column whatsoever, it still takes a finite amount of time to reach the detector after traveling through the column. So this amount of time is demarcated T0, and the term used to describe this is the dead time of the column. So the reason I bring up this dead time of the column is because the various parameters that we'll be calculating in the next few slides all make reference to this dead time. So the dead time of the column is the finite amount of time that it takes for the mobile phase, which is completely not interacting and being retained on the column, to travel through the column and to reach the detector. So the first factor that evaluates column suitability is the retention factor. The retention factor quite simply tells us for a particular chemical component, is it very highly retained, which means that it interacts with the column a lot, or is it not that highly retained, so it interacts with the column just a little bit. So of course, a large retention factor will indicate that there's a lot of interaction, and therefore we have increased separation. But the trade-off is that it also have a much larger elution time. So the retention factor is defined for each chemical component, and we take the retention time of that chemical component minus the dead time, expressed as a ratio of T0, the dead time. Okay, so of course, the larger the retention time, you'll get a larger K prime, which is the larger retention factor. So that quite simply tells us that the particular chemical component in the sample mixture interacts a lot with the stationary phase, thereby taking a much longer time to travel through the column and to reach the detector. Now, in addition to how much the chemical component interacts, several parameters can also be adjusted to change the retention factor. For example, column length is one of them. If you increase the column length, obviously it will take a longer time for the compound to travel through the column and reach the detector, right? Because it's going to have a lot of opportunity to interact with a longer column. So therefore, its retention time is going to be much larger. Earlier, we also talked about how different columns have different thickness in terms of their films. So they may have a very thin film of stationary phase, or they may have a very thick film of stationary phase. Of course, if you increase the thickness of the film, or increase the thickness of the stationary phase, there's going to be more opportunity for your chemical component to interact, and therefore its retention time is also going to be larger, and therefore its retention factor, the K prime, is also going to be larger. Now the second is the selectivity factor. The selectivity factor of a column indicates the ability of the column to differentiate between two compounds, namely B and A. So this is the ratio of the K primes of two adjacent peaks. So for example, we have a peak B and a peak A. If we take the K prime of the peak B divided by the K prime of the peak A, that will give us the selectivity factor. And what we would like is for the selectivity factor to be greater than 1. If the selectivity factor is 1, it means that the column is actually unable to differentiate between compound B and compound A, because what it means is that based on the equation, the retention time of compound B is actually the same as the retention time of compound A. Only then can we get the selectivity factor of 1, right? So if that's the case, that means that the column is completely unable to separate B from A. It is completely unable to differentiate B from A. So what that tells us is that if that is the case, that column is definitely not suitable for that particular analysis. What we would like, therefore, is that the selectivity factor is somewhat greater than 1. Because if it's greater than 1, it means that the column is very well able to differentiate or separate B from A. Of course, the larger the selectivity factor, the better, because it means that the ease of separation or the ease of differentiating between these two compounds is much better when we use this column. Now, the last parameter that we use to look at column suitability is an idea called column efficiency. Column efficiency is defined as the ability of a column to give us narrow peaks. So therefore, if a column is very efficient, we say that the column is very well able to give us very narrow peaks, and therefore it's very likely that the resolution of our peaks, the separation of our peaks, will be very good. So of course, a highly efficient column is quite desirable. Now, the measure or the quantitative measure of column efficiency is something we call the number of theoretical plates, given the alphabet n. And n is calculated by 16 times the retention time of the peak divided by the peak width, whole term squared. Okay, so of course, although the number of theoretical plates sounds very funny, if we have a larger number of theoretical plates, that would indicate that we have a more efficient column. Now allow me to just explain what this idea of theoretical plates are. Okay, recall that the number of theoretical plates is a concept that we use to describe how efficient a column is in terms of separation and giving us narrow peaks. Okay, so the larger the number of theoretical plates, the more efficient the column is at giving us narrow peaks. Now we can think about theoretical plates this way. If we look at our top schematic, we see the mixture of blue molecules and red molecules traveling through our column. And we can imagine these 4 theoretical plates, places where the various molecules can interact with the stationary phase. Okay, so we imagine that it's flowing through the column, and at these 4 stages, or at these 4 plates, it has the opportunity to interact with the stationary phase and therefore generate some amount of separation. Okay, so of course, if we look at the bottom schematic and we have many more theoretical plates, this means that there are many more sites at which interaction with the stationary phase can occur, and therefore separation can occur. So logic tells us that the bottom schematic actually represents a column that has much better separation, because there are many more sites where the interaction or separation can occur, and therefore the column at the bottom is very likely to generate narrower peaks, more efficient type of separation. Now, this is one way to visualize the idea of theoretical plates. It's important to remind ourselves that this is not what a column actually looks like, right? So every column does not actually have plates along its length where the interaction occurs, right? We talked about what a column looks like. There's actually a coating on the inner surface, and that acts as the stationary phase for which separation occurs. But I do find that this schematic is a good idea to visualize this idea of theoretical plates. The more plates you have, it's an indication that you have a column that has greater separation efficiency, and it's more likely to lead to narrower peaks. Now, another measure of column efficiency is directly related to the number of theoretical plates, and that is the plate height, H. So sometimes some textbooks use plate height as opposed to number of theoretical plates, and the plate height is quite simply defined as the length of the column, typically in meters, divided by the number of theoretical plates. So the reason for using plate height is that in the world there are many different columns of different lengths, so therefore sometimes it is difficult to just use the number of theoretical plates to compare, because if you compare a column that is 10 meters versus a column that is 30 meters, of course the 30-meter one is more likely to have a larger number of theoretical plates, so it's a bit hard to compare. But if we take the length and we divide by the number of theoretical plates, using the plate height H, we can then compare the efficiencies of columns of different lengths. So as an example, we're told that we have a chromatography analysis of a pesticide, and it gives us a peak of 8.68 minutes retention time, and the width is 0.29 meters. So quite simply, we are asked to calculate the number of theoretical plates and also calculate the plate height. So the number of theoretical plates, we just put it into the formula, right? So it's 16 times the retention time divided by the peak width, and then whole term squared. So it comes up to 14,334 theoretical plates, right? And then for the second part, we are told that the length of the column is 10 meters. And so if we take the length divided by n, we should get the theoretical plate height, which is 6.976, 10 to the minus 4 meters. So what this actually allows us to do is that if we have another column and we are able to calculate the H, or the theoretical plate height of that other column, then quite simply we can put these two side by side and figure out which is a better column for this analysis. Which column actually gives us a better separation efficiency? Obviously, the column that has a smaller H number will indicate better separation efficiency, and will definitely tell us that that is a more suitable column for use for this analysis.